So today let's begin by looking at earthquakes, and so this table here here's a table about the most notable earthquakes over the last several centuries, going back to the year 856, and possibly the greatest natural disaster of all time was the earthquake that occurred in 1290 in China, where about 1556 in China, where 830,000 people are thought to have been killed. And so this is a very important topic for not only geologists, but for a civilization as a whole, because obviously the idea with earthquakes is something that everybody needs to be concerned with. So let's begin by defining what is an earthquake. An earthquake is simply the vibration of the earth produced by a rapid release of energy. And the energy released radiates in all directions from its source, called the focus or the hypocenter. And the energy in turn is in the form of waves. And from there, sensitive instruments called seismographs that are positioned around the world can then record the event. So here we have a block diagram showing a fault. And by definition, the hypocenter is that position within the fault where the initial fault slippage occurs. And if we project the hypocenter to the surface, we can plot what's called the epicenter, which is simply the point on the surface directly above the hypocenter. And from there, the energy travels away from the hypocenter in what are called seismic waves. Now, the best way to understand earthquakes is by considering what's known as the elastic rebound theory. And according to this theory, the fault plane is initially at rest, and this can be equated by holding a limber stick in the initial relaxed position. But then, as force is applied or stress is applied, the fault is initially locked and resists movement. And with continued stress, this causes elastic energy to build up into rocks around the fault. And this equates to the bending of that limber stick. But then eventually the fault finally slips, releasing energy as seismic waves to generate a earthquake. Afterwards, the fault returns to its initial state, but the fault block is now displaced. So here, for an example, we see slippage along a fault. And if you follow the trees within this orange grove, you can see the actual offset within the trees, and which looks like to be a strike-slip type of movement. And in the inset, in turn, we see how a fence was offset about 2.5 meters or 8.5 feet during the 1906 San Francisco earthquake. So in this case, we can actually measure the amount of displacement at this location, assuming that the fault movement was entirely strike-slip. Now, when the earthquake occurs, it's not the entire fault that slips. Instead, initial slippage begins within a small portion of the fault plane known as the hypocenter. And within this block diagram, the initial area of slippage is outlined by that reddish, by that circle that's color-coded red that immediately surrounds the hypocenter. But then the rupture surface will begin to propagate or travel along the actual fault surface at a rate of about 2 to 3 kilometers per second. And the rupture surface then continues to grow until it finally reaches a section of the fault where the rocks have not been sufficiently strained. And at that point, the overall slippage kind of fizzles out and stops beyond that particular range. Now, a major earthquake may be preceded by a series of smaller earthquakes that are called foreshocks. And these foreshocks occur as strain builds up along the fault plane. But then finally, the strain reaches the point where the fault slips, and this produces the main earthquake. Following the main slippage, small tremors called aftershocks may occur over days to months following the main earthquake. And these aftershocks mainly reflect the fault as it readjusts following the main slippage event. Now, we saw before that the energy released from the area of fault slippage travels outward as these intense vibrations called seismic waves. And it's the seismic waves that cause the ground around the area of a slippage to shake violently, producing what's known as an earthquake. Now, seismographs are instruments that record the movement of the ground in relation to a stationary object, mainly on a rotating drum or possibly on a magnetic tape. And a typical seismic observatory will measure three components of the ground motion. We'll have the vertical up-down motion. There may be an instrument that measures the vertical up-down motion. And then at the same observatory, there'll be a second instrument that measures the horizontal east-west motion, and even a third instrument that measures the horizontal north-south motion. And these three different components of the ground shaking are all recorded at the same seismic observatory, and we have these observatories positioned all around the world. Here, for an example, we see a seismograph configuration for measuring the horizontal east-west or a horizontal north-south motion of an earthquake. And notice that the instrument itself is anchored to the bedrock. And it's best to actually drill a hole into the bedrock and position the instrument deep within the bedrock in order that the instrument is not affected by extraneous noises, as, for example, the vibration of passing cars or perhaps a thunderstorm, things of that nature. And within this configuration, the instrument will mainly record vibrations within the bedrock itself, primarily as a result of a earthquake. Now, in this configuration, this instrument is going to, this seismograph is going to measure the horizontal component of the ground motion. And here we have a support and a pivot, and there's a weight at the end of the pivot which holds a pen, and this pen in turn is suspended by a wire. And notice that the pen touches upon a slowly rotating drum that's wrapped with chart paper. So in this configuration, as the ground shakes, as the horizontal component of the ground's motion occurs, this in turn will be recorded by these squiggles on the chart paper. They can probably retrieve the data in this, but in actuality, today's seismograph instruments are record digitally, and that information is then sent to servers, and people access it on a computer. But this is just to show the basic idea of how these earthquakes are recorded. Here's another configuration, a seismograph configuration for measuring the vertical up-down motion of an earthquake, where the base is again anchored to the bedrock. And now we have a vertical support with a hinge that's supporting a suspended mass. But anyway, here we have a situation. We have a cutaway view of the Earth with the core, the mantle, and the surface. The focus is also known as the hypocenter. Again, it's the position of initial slippage on the fault plane. But notice that the seismic waves travel away from the focus in three distinct groups. First of all, we have the surface waves that travel right along the surface. And notice that we have additional groups that travel within the mantle itself. These are called body waves and include P waves and S waves. But ultimately, these three different or distinct groups will arrive at a seismograph station located at some distance from the focus. But if you look closely, we notice that the three groups are traveling at different velocities and will arrive at that seismograph station at different times. And here in this figure towards the right, we have a typical seismogram recording. We can envision this seismogram as having been recorded on that chart paper, on that rotating drum. And notice that it's scaled in minutes, ranging from 0 to 50 minutes, going from left to right. Now, when these three distinct groups are passing either along the surface or through the mantle, the first group to arrive at that seismograph station are what are called P waves. P waves travel the fastest, and at this particular station will arrive about 3 minutes after the initial fault slippage. The second group to arrive are what are called S waves, and in this case, the S waves will arrive about 10 minutes after the earthquake. And the final group to arrive are the surface waves, which are the slowest. And in this particular situation, the surface waves will arrive at this seismograph station about 30 minutes after the earthquake. Does everybody see this? Okay. So if we unwrap that chart paper from that rotating drum and spread it out, notice that the chart paper is marked off in intervals of 1 minute, and this is shown down here. So the spacing between each of these pairs of vertical lines is equivalent to a time of 1 minute. And so here to the left we see the first P wave arriving, and then further towards the right we see the first S wave, and then finally later on the surface waves will finally be recorded at this particular station. The actual timing of arrivals depends on where the seismograph station is located and its distance from the hypocenter. Now, an important thing to point out at this point is that we can actually measure the time interval between the first P wave and the first S wave simply by counting the 1 minute intervals in between. So, for example, we have a half a minute here, so this is 1.5 minutes, 2.5, 3.5, 4.5, and then finally 5. So there's about a 5-minute time interval between the first P wave and the first S wave. And this time interval is very important because as we see as we go along, this will allow us to actually calculate the distance of this particular seismograph station from the hypocenter of the earthquake. But first of all, let's Okay, here's another perspective. Here's the cutaway view of the Earth. For convenience, the epicenter is close to the North Pole. And from there, we have these three different groups of seismic waves traveling away from the epicenter. At seismograph station 1, which is the closest, notice that all three waves have arrived at this point, the P waves, S waves, and surface waves. Further from the epicenter, here's seismograph 2, which has also recorded the arrival of all three of these waves. But notice that seismograph station 3, located at the farthest from the epicenter, only the P waves have reached that seismograph station 3 at this point. The S waves and the surface waves have yet to arrive. And these groups will eventually arrive several minutes or tens of minutes later. Another important thing to note is that as we travel further from the epicenter, notice that the distance between the P waves and S waves gradually become greater and greater the further away from the epicenter we go. And again, we're going to look at this in more detail and see how we can determine the distance of each of these stations from the epicenter using this separation between P and S waves. But first of all, let's look at these different groups of seismic waves in more detail, beginning with P waves. P waves are referred to as primary waves that travel through solid rock at an average velocity of about 5 kilometers per second. Now, the actual velocity of P waves depends on the material through which it's traveling. Through unconsolidated sediment, P waves will travel slower, whereas in denser mantle, P waves will travel faster. So this is just kind of an average velocity. Now, P waves not only travel through solids, but can also travel through liquids and even gases. And these P waves travel by pushing or pulling particles of matter in the direction of the travel path. And this is illustrated by this example of a slinky. Notice that we can attach one end of the slinky to the wall and then pull it horizontal and then give the slinky a push. The wave direction will be from the hand towards the wall, or in other words, from left to right. And the waves will travel as a series of expansions and contractions, such that the particle motion is back and forth in a direction horizontal to the overall wave direction of travel. And this is how P waves travel through Earth materials, as shown in the block diagram towards the right. Essentially a series of compressions and expansions, particle motions parallel to the overall direction of wave travel. Does everybody see this? Yeah. The grid on the right, we start out with equal squares. And then notice that as the P wave travels from left to right in that block diagram, the squares undergo a succession of compressions and expansions. Now, for example, at one particular time point, that portion of the crust is being squeezed, but then about a second later it's undergoing expansion, and then it's back to contraction and expansion. And this is the way that P waves travel through the rock or sediment. Now, S waves are known as secondary waves. They travel through solid rock at about half the speed of P waves. S waves are also called shear waves because they push material at right angles or at 90 degrees to the overall path of travel. And unlike P waves, shear waves cannot pass through liquids or gases. S waves can only travel through solids. To illustrate the motion of S waves, we can take a rope and tie one end of the rope to the wall and then pull it horizontal. And in this case, we give the rope a shake. And notice in this, again, is the particle motion or wave direction is from left to right. The particle motion in this case is perpendicular or up and down at 90 degrees to the overall direction of wave travel. And this is the way that secondary waves travel through materials. Okay? Now, surface waves, on the other hand, are confined to the surface and outer layers of the Earth and travel at speeds slightly less than that of S waves. Now, some surface waves are similar to waves in the ocean, as, for example, this upper block diagram. And notice as in the upper diagram, we see that as the S waves travel through the upper crust, the material itself exhibits a kind of a rolling motion in a counterclockwise direction, similar to the rolling of ocean waves. Another type of surface wave, as shown in the bottom, exhibits this side-to-side motion. But in either case, surface waves tend to do the most destruction during an earthquake. As a matter of fact, during very strong earthquakes, maybe earthquakes exceeding magnitude 7.5 or 8, there's been reports of people actually seeing the ground roll like waves in the ocean, and that's due to the passage of a surface wave. So, as I showed before, seismologists can measure the time interval between the first arrival of P and S waves to determine how far away the epicenter is to a particular seismograph station. So here we have three different examples of seismograms, one from New York, a second one from Nome, Alaska, and the third from Mexico City, Mexico. And in all three of these seismograms, the first P wave and the first S wave positions are indicated. I think in seismograms B, the first S wave is not labeled correctly. This is from the textbook. I think in seismogram B, they're actually labeling the arrival of the surface wave. But seismogram A and C are correctly labeled, so anyway. So let's determine the distance of the epicenter from New York. So looking at the seismogram A from New York in the left part of the figure, we see the position of the first P wave and the first S wave. And again, we can count off these intervals marked off by these vertical lines to actually measure the time between those two arrivals. So we have 1 minute, 2 minute, 3 minutes, 4 minutes. So there's about a 5-minute time interval between the first P wave arrival and the first S wave arrival. Now in the graph to the right, which is in coordinates of time in minutes in the vertical scale versus distance from the epicenter in the horizontal scale, we have two curves. We have the travel curve for S waves and the travel curve for P waves. Now at the epicenter itself, these two curves converge, so that if we had a seismograph station located directly on the epicenter, the S wave and the P wave will be recorded simultaneously. There's no separation interval. But as you move further away from this epicenter, notice that the time interval between these two curves becomes greater and greater the further we go. Now, we determined at New York that that time interval was 5 minutes, so what we do here on the right is find that position on the graph where the separation between the S curve and the P wave curve is 5 minutes, and that's marked, okay? Does everybody see this? And from there, we simply read down to the horizontal scale, and we see that New York is about 3,700 kilometers from the epicenter. Okay. Everybody see this? On the other hand, a seismograph station closer to the epicenter, that time interval will be much shorter. Okay. So what do we do with this? We know that New York is 3,700 kilometers from the epicenter, but we do not know the direction of the epicenter from New York. It could be anywhere within a 360 degree. So here's New York, and New York is located 3,700 kilometers from the epicenter. So what we do is draw a great circle around New York with a radius of 3,700 kilometers. So this tells us that somewhere along that great circle is the epicenter. Now, just looking at New York alone, we can't really determine where the epicenter is, only its distance. What we need is at least 2 other seismograms at different locations in order to determine, to triangulate the actual position of the epicenter. And using similar techniques, we find that Nome, Alaska is located 4,400 kilometers from the epicenter, so we construct a great circle around Nome with a radius of 4,400 kilometers. And then we also have a third seismogram at Mexico City, where we construct a great circle of 1,800 or 2,900 kilometers based on its seismogram profile. Now, the intersection of all 3 of those great circles will locate the epicenter of the earthquake, and it occurred somewhere in the western U.S. as indicated by this star. So in order to do this, we need at least 3 stations, preferably many more, in order to triangulate the actual position of the epicenter. Does everybody see this? Okay.
Why specifically 3 to locate the epicenter?
Well, if you only had 2 great circles, then you have 2 intersections, and so you have 2 solutions. Only one great circle would not tell you much of anything. It could be anywhere within the 360 degree radius around New York. You need at least 3 intersection of 3 great circles in order to find a common point of intersection. So you see that we can, once we pinpoint the epicenter of an earthquake, the next step is to measure the size of the earthquake. And 2 measurements that do describe an earthquake size are the intensity scale, which is a measure of the degree of earthquake shaking at a given locality based on the amount of damage. And there's a second scale, which we're more familiar with, which is the magnitude, Richter magnitude, which estimates the amount of energy released at the source of the earthquake. Let's first of all look at the modified Mercalli intensity scale based on the amount of damage. And notice that in this case we use Roman numerals ranging from 1 to 12, where 1 is the weakest and 12 is the strongest. And if you look at the descriptions next to each one of those intensities, basically we're looking at the amount of damage, whether or not people have felt the earthquake. For example, in intensity 7, we get considerable destruction in poorly built buildings or badly designed structures, whereas well-built ordinary structures will receive slight to moderate damage, and so on and so on. The greatest intensity, 12, refers to total damage, where waves can actually be seen on the ground surface. Those are the surface waves we looked at earlier, to the point that objects are literally thrown upward into the air. So anyway, this is how the modified Mercalli intensity scale is measured. The problem with the intensity scale is that earthquake destruction depends on many factors that include, for example, the overall size of the earthquake, the duration of the ground shaking, the strength of the buildings, the distance from the epicenter, and even the nature and of the soil and the bedrock. But in general, buildings resting on unconsolidated soil tend to experience more damage than buildings constructed on solid bedrock. And we'll see some examples of this. Here's a map of intensity resulting from the Loma Prieta earthquake in California back in 1989. The epicenter occurred just to the east of Santa Cruz. And if you look at the color scale, the maximum intensity is assigned the intensity of 8, which occurs directly around Santa Cruz. And if you follow the color codes, the intensity decreases as we move away from the epicenter, as we would expect. However, if you look near Reno, we have slightly higher intensities within this overall region of lower intensity, even though it's at the same distance from the epicenter. So we see right away there are problems with this overall intensity assignment. Here's another problem with the intensity scale. Here's the in the inset in the lower right, the earthquake epicenter is plotted with that red star, and we're going to look at a enlarged portion of the San Francisco Oakland area, and in particular at 3 different seismograph stations indicated by these black dots. Now, for all practical purposes, we can consider these stations at pretty much the same distance from the epicenter. On the other hand, if we look at the seismograms, we see quite a bit different amplitudes in the amount of ground shaking. For example, the greatest amplitude occurs at the seismograph station located on sitting on soft mud. There's also quite a bit of ground shaking at the location underlain by sand and gravel, whereas the amplitude is very, very low for the seismograph station located on solid bedrock. And this is a good demonstration of how the nature of the soil and bedrock has a lot to do with the overall amplitude of ground motion. Again, If buildings sitting on soft mud or sand and gravel are going to experience a lot more destruction relative to buildings that are sitting upon solid bedrock. Here are a couple of photographs. This is the aftermath, again, of the Loma Prieta earthquake of 1989 within the Marina District of San Francisco. And if you look in the foreground, the question is, why so much damage for an intensity 7 earthquake? If you look in the background, those buildings are in pretty good shape, whereas the buildings in the foreground are completely destroyed. Why?
It's because of the building's specific
It,
construction.
well, the actual reason is because buildings in the foreground are resting on former landfill, whereas those in the background have a more sturdy substrate.
What about that?
Here's an interesting situation. The green dots on this national map show the locations of people who reported feeling earthquakes of similar magnitude. One earthquake located in central California and the other occurring in central Virginia. Now, even though the earthquake in central California with the magnitude 6 was a little bit stronger than the one occurring in central Virginia, the distribution, the regional distribution of people feeling that earthquake was quite a bit less than the distribution of people feeling the earthquake in central Virginia. And the difference is attributable to the actual rigidity of the bedrock. The bedrock within the eastern states was such that the magnitude was felt over a much larger area, basically. And again, this just demonstrates how the underlying bedrock or substrate has a lot to do with whether or not people feel the earthquake, at what distance, and how much damage is done. There's a lot of different factors go into that. Any questions on this? Okay. Now, other types of destruction from seismic vibrations include liquefaction, and this is when the ground shaking draws groundwater up to the surface, such that unconsolidated soils become saturated with water and, for the most part, turn into a mobile slurry no longer capable of supporting structures. There are also what are called saichis, where the shaking causes rhythmic sloshing of water within lakes, reservoirs, enclosed basins, to the point where the waves can weaken and destroy the reservoir walls. Quite often, dams tend to give way as a result of that sloshing within that reservoir behind the dam. These are sand volcanoes resulting from liquefaction, again resulting from the Loma Prieta earthquake of 1989. And if you look at the bottom figures, we see that before the earthquake there was a loose, saturated sandy material within the underlying well-packed soil. But then during the earthquake, the water and upper sandy layer was mobilized and literally erupted on the surface as these little sand volcanoes shown in the upper photograph. And this is what occurs in liquefaction overall. The shaking causes the overlying sandy material to become saturated to the point that it, for the most part, turns into quicksand, no longer capable of supporting the overlying structures. And as a result, the structures will then simply sink into the ground. as occurred in the 1985 Mexican earthquake. Mexico City sits on an old lake bed, underlain by unconsolidated material, so this is why there was so much damage as a result. And here's another example how destructiveness, in this case, depends on the strength of the building. A well-constructed building to the left has, for the most part, survived intact, whereas the one on the right has completely has been completely demolished. So the point is that the intensity scale is not a very good scale. Oh, this is our favorite slide. This means end of lecture for this point.